Okay, now we're going to talk a little bit about nuclear equations. So notice that when you write your nuclear equation, when we write down our isotope, we not only have our symbol, but we also include our atomic number down in the lower left and our mass number in the upper left. And the reason looks like this. When uranium-238 decays, it emits an alpha particle. And an alpha particle is basically a helium nuclide. The sum of my protons must equal the sum of my protons on the left is equal to the right. The sum of my mass numbers on the left must equal the mass number on my right. Therefore, if I say that I am emitting an alpha particle, this is an alpha decay or alpha emission. Then we know that we're losing a helium nuclide. So once we have that, we know this has to be thorium-234. So let's try another example. What happens if we have an alpha decay of, let's say, radium-226? So the way we write that down, we have radium, and we look and we say, oh, there are 88 protons in the radium. My isotope is 226. I have an alpha decay, so we know that's a helium nuclide. So we know that I have to have 86 protons here, and it's 222 for my mass number there. And when you look up what has 86 protons, it's radon. So now we know that radium-226 has an alpha decay to give you radon-222. Okay, so that's an alpha decay. So before we continue, let's talk about the different types of particles that can be emitted. So, the types of radiation. And then we can go back into our nuclear equations. The types of radiation is we have alpha radiation, we have beta radiation, we have gamma, we have a positron emission, and I'll mention this, but it's not really radiation. We also have electron capture. So we'll talk about the radiation, which is these four, and we'll talk about the types of nuclear reactions, of which this will be included. Okay. So when we talked about the radiation, let's talk about their charge. Okay. And we'll talk about their mass. Okay. And then basically the nature. And I'll mention verbally what the penetrating power is and explain what that means. So the charge of an alpha proton, or our alpha particle, is a +2. The mass is actually 6.64 times 10 to the minus 24 grams. And what is its nature? Well, we know an alpha particle is a helium nuclide. Okay, the penetration power, relative penetration power of an alpha particle will set to 1, which means it gets stopped at your skin. So it will basically penetrate through a couple layers of skin, but after that it gets stopped. The beta particle has a charge of -1, Okay, the mass here is 9.11 times 10 to the minus 28 grams, and the nature is an electron. Okay, so it's a high speed electron. Okay, and what that means is basically with a relative penetration power of 100, it can enter soft tissue. The gamma radiation has zero charge, has zero mass. What it is, it's a photon. And so we know it's the highest energy photon. It's basically a gamma ray that we're talking about. Positron here has a charge of a +1. Okay, and sometimes you'll see us write beta as a beta minus for a beta particle. Positron, okay, is a beta plus, has a +1 charge. Mass is similar to an electron. It's the 9.11 times 10 to the minus 28. Okay, and the nature, okay, it's a positron. So we write it like this as well. It's also called a positron. Okay, for the electron capture, when we talk about those nuclear reactions, just so you know, the electron is a orbital electron. So it's a slow moving electron that we're talking about. Okay, now that we know the types and your gamma radiation has a penetrating power of basically 10,000. It can go through tissue and basically dense material in your body like bone as well. Okay, so let's start talking about the different types of nuclear reactions. Okay, the first you already encountered. One is alpha decay. So I'll just rewrite up the example that we used earlier. This is also another way you can write your reaction by saying, instead of writing the helium nuclide, you can just say alpha. Okay. The second one is called beta emission or a beta decay. An example of that would be iodine 131. And when it undergoes a beta emission, you're losing a high-speed electron. So this has a sum to 53. This is 131. What we find is it goes to xenon. Okay. The third, the gamma radiation, because there's no mass and no charge, they are not included in our nuclear equations. They really don't affect what we write down for our nuclear equations, which is why we don't include them. But just so you know, gamma radiation pretty much accompanies all nuclear equations. Okay. The fourth is our positron emission. And we use this actually, if you ever hear of PET, which is positron emission topography, we use that in the analysis actually of people who have cancer and other types of diseases, that we can use this as well. Okay, so if we look at this, let's take a look at carbon 11, and if this undergoes a positron emission, then this plus 5 and 11, this means when we get a positron decay, we form boron 11. Okay? Also, let's talk about electron capture. Okay? The electron capture Let's take something like a heavier element. That's rubidium-81. And it captures an orbital electron. So because it's a capture, notice this is on the reactant side. And what we form, 36, 81, is we get krypton, 81. Okay? So, in general, let's talk about what these will produce. If you look at one, my alpha decay, all it's done is you lose 2 protons and 2 neutrons from the reactant, okay? Okay, we'll talk about why that's important. When we look at beta radiation, I'm now going to use different symbols here. If I take something like a neutron, okay, this is the symbol for neutron, no charge, massive 1, and it undergoes beta radiation. Then the way to get this plus a 1 to get a 0, this plus a 1 to get a 1. Well, what particle is this? It's a proton. So beta radiation is a way to convert a neutron to a proton. Okay, then gamma doesn't affect us. So let's take a look at the fourth one. We were talking about positron and electron emission and electron capture. So when we look at positron, make sure I put my lines there, emission. Let's take a look at my proton. If I emit positron, then this has to be a 0. This has to be a 1. Oh, that's a neutron. So if I take a proton and do positron emission, I form neutrons. So this is a way to convert protons to neutrons. Okay? Let's also talk about electron capture as well. So if I do electron capture, it's the same thing, right? I take a proton, I capture an electron, and what I get is a neutron. So these are different ways that our atom nucleus can now, our nuclei can either reduce overall the charge and its mass by losing 2 protons, 2 neutrons. I can convert from neutrons to protons, or I can convert from protons to neutrons. So why is that essential? So let's talk about patterns of nuclear stability.